So let P2 RD be the set of mu Borel probability measure on RD such that the second moment of mu is finite. And recall that if mu naught, mu 1 are in P2 of RD, gamma mu naught, mu 1 is the set of gamma probability measure on RD cross RD that are Borel such that the first projection of gamma is mu naught and the second projection of gamma is mu 1. So this means that if you compute mu naught of A, it is the same thing as computing gamma of A cross RD, which is also equivalent to if you integrate a function phi d mu naught, it is the same thing as integrating the function in the first variable, gamma dx dy, RD cross RD. So take C of xy to be 1/2 x minus y squared. The Wasserstein distance between mu naught and mu 1 is the infimum, gamma having mu naught and mu 1 as marginal, the integral over RD cross RD of x minus y squared, gamma dx dy, and so it is 2c xy is the cos 2c sy I am using. So we want to study the following equation. Given h greater than 0, u in RD, theta greater than 0, minimize the Wasserstein distance, and given f naught, a probability measure on RD of bounded second moment, minimize the distance square between f and f naught plus h s of f, where s of f is the negative entropy, the integral of f log f over RD, subject to the constraint that the first moment of f is u, and the temperature of f is theta. And next time on Monday, we are going to write the Euler-Lagrange equation of this and see that it is the discrete form of a Fokker-Planck equation if I choose h appropriately. So now let us make the following observation. Set mu naught to be the Dirac mass at u, and mu 1 to be the Lebesgue measure with density f. Then this set gamma reduces to one element, gamma of mu naught, mu 1 equal to mu naught rho dot mu 1. It contains only one element because you have a point somewhere and you have mass distributed somewhere else. You are looking for the way to transport the point, the mass here to that point. There is only one way, there is only one point. And so, as a consequence, if I compute W2 between delta U and F dx, I get that it is the integral of this. So it is the integral over Rd of V minus U square F of V dV, which is d theta F. So imposing this condition is equivalent to imposing that we are restricting ourselves to the sphere of center delta U and radius d theta.
Theta F is again the variance?
Yes, theta F is by definition 1 over d the variance. It is by definition 1 over d the variance. Okay, so I've been calling this a distance. I am going to write the Euler-Lagrange equation of this later. So there are a few things I need to do to show you that this is a metric. And there are a few things I need to do to show you how to compute the Euler-Lagrange equation. So let me start with this first observation.
The F in this case is just density. It's a function, not a measure, right?
It is a function.
A function.
So,
measure.
yes, so f dx is a measure. And I'm going to use the abuse of language, of notation. Instead of f dx, f naught dx, I am going to just write f naught.
But so F0, you put F0 belong to P2 of R3. P2 are
The set of probability measure of bounded second moment.
But it's still a function also, right? F0.
Yes, f0 is a function. So
Set of probability in RD whose second moment is finite.
yes, second moment is finite. Yeah. So the P2 is justified by the following fact. I want to ensure that this is not identically plus infinity, given mu naught and mu 1. But I can take gamma to be mu naught, mu 1. Then this is less than the integral of x squared plus y squared twice gamma dx dy. The first integral will give twice the integral of s squared mu naught ds. And the second integral will give the integral of y squared mu 1 dy over Rd. And so if I assume that mu naught and mu 1 are in P2, meaning the second moment is finite, it ensures that there is at least one gamma for which this functional is finite. And so the problem I am studying is not a trivial problem. The functional I am minimizing is not identically plus infinity. So let me remind a few of the facts we done last time. Call this one. Call 2. Consider also Monge problem, which is the infimum over t, the integral over rd of x minus t of x square mu naught ds, subject to the constraint that t pushes mu naught forward to mu1, and that t from rd to rd is Borel. Okay, so let me remind what we have obtained. If mu naught is absolutely continuous with respect to Lebesgue measure, then 1 has a unique minimizer. Gamma bar. 2 has a unique minimizer. T bar. Gamma bar is identity cross T bar, push forward mu naught. And there exists V from RD to negative infinity plus infinity, such that UC equal to, if I set V to be UC, UC is also V, and gradient U of x equal to gradient H of x minus T bar of x, mu almost everywhere. Okay, so let me recall briefly how this was established. We look at the integral of u d mu naught plus the integral of v d mu 1 under the condition u plus v is less than c. And on the support of the gamma optimal, we necessarily have u of s plus v of y equal to c of xy. Then we're differentiating the left-hand side with respect to x to obtain that it is the derivative of the right-hand side with respect to y. And that is what I have written. And y is uniquely determined by y equal to the gradient H inverse x minus the gradient H inverse of the gradient of u of x. And that was the optimal map that pushes mu naught forward to mu 1. Okay. So here are some conclusions I would like to draw. Let me call that this V bar, U bar, V bar, U bar, V bar. let me write what this means. By 3, u bar of x is the nth y in RD of x minus y squared over 2 minus v of y. Okay? This is what the C, this is what the VC, the C concave transform is when C equal to x minus y squared over 2. Now I am going to expand this to have that it is the infimum y in RD of s squared over 2 minus xy plus y squared over 2 minus v of y. I can take the s out, and I am going to set this to be psi of y. So what I see is, I see that s squared over 2 minus u of x is the supremum y in RD, because when I multiply u bar by negative, I multiply the infimum by negative, it becomes a supremum, and this becomes a plus xy minus psi of y bar. This is what I have. And call this by definition phi bar of s. I see that phi bar of s is a supremum of linear function in S. Therefore, it is a convex and lower semi-continuous as a supremum of convex and lower semi-continuous function. Thus, C bar equal to phi bar star, and so it is convex and lower semi-continuous as a supremum of lower semi-continuous function. Now, let me come back here. This is x minus t bar of x. So call this 4. By 4, t bar of x is x minus the gradient of u bar of x, which is the gradient of phi bar of x. So I have just written that the t bar is the gradient of a convex function. The property t bar pushes mu naught forward to mu 1 if mu naught is f naught ds, mu 1 is f1 dy. Assume that t bar was 1 to 1. This will be equivalent to f1 gradient phi bar of x. The determinant of the Hessian of x equal to f naught of x, with the property that the gradient of phi bar send the support of f naught to the support of f1. So that is the Monge-Ampère problem of second type. Monge-Ampère problem of the first type, you impose Dirichlet condition. Monge-Ampère problem of the second type, you impose that the range of the gradient of phi bar is prescribed. Okay, so let me summarize what we have learned from all of this. The summary, let me state it as a corollary. Assume mu0, mu1 are two probability measures on RD, and mu0 is absolutely continuous with respect to Lebesgue measure. Let T from RD to RD be a Borel map such that T pushes mu0 forward to mu1. Okay. So T satisfies the first condition to be one of the candidates when I am minimizing my functional in Monge problem. Then T minimizes the Monge problem, which is 2. If and only if there exists a function phi from RD to negative infinity plus infinity, convex, lower semi-continuous, semi-continuous, such that T is the gradient of a convex function. So what this is saying is the following. You choose an arbitrary convex function. You choose a mu0, which is absolutely continuous with respect to Lebesgue measure. You define mu1 to be mu1 pushed forward by the gradient of phi. Then this gradient is the optimal map, the unique optimal map when you are solving this problem. So again, the analogy is what I have written with geodesic. I mean, geodesic on a Riemannian manifold are characterized by a certain equation. They are critical points of a certain action. And when you look on a short length, being a curve of minimal length is equivalent to being a geodesic. So this is the analog of that result. So let me briefly prove this and show that it is a consequence of what I just wrote on the board. First, assume T minimizes 2. Then it is written here that the minimizer is unique. It is T bar, and T bar, call this 5, and T bar is a gradient of a convex function. Then
this result is by Bernier, this one, this corollary. Is this the
yes, yes. Then T equal to the gradient of phi star by 5, by the remark, by the remainder.
This basically was the start of everything.
Yes.
This was the base and this central.
Yes.
That there is this relation between this minimizing the Monge problem and finding this function, convex function with gradient.
Yes. Yes. And the fact that this theorem, the fact that T is the gradient of a convex function is instrumental when you try to connect the Monge-Kantorovich theory to PDE. We will see that it is heavily used when you are trying to write the Euler-Lagrange. When you are trying to show that the Euler-Lagrange equation of this is the discretization of the Fokker-Planck equation. Conversely, assume T is the gradient of phi, where phi is from RD to negative infinity plus infinity, is convex, and upper and lower semi-continuous. Okay. So writing this means that the gradient of phi exists mu almost everywhere. We have the following property. If you write phi of x plus phi star of y, where phi star is the Legendre transform, this is always greater than or equal to xy. Equality holds if and only if S is in the subdifferential of phi star at y, which is also equivalent to y is in the subdifferential of phi at x. Okay, so these two properties are equivalent. But when phi is differentiable at S, the subdifferential reduces to the gradient. So it means that at point of differentiability, I have phi of x plus phi star of the gradient of phi of x equal to x, the gradient of phi of x, if the gradient of phi of x exists. So this statement was part of the homework problem, and I gave some idea on how to prove them. So let me write what this means. By assumption, we are assuming that T is the gradient of phi. Hence, negative phi of x minus phi star of T of x equal to negative x, the gradient, negative f T of x. Okay, I just rewrote what is there. Now I'm going to add s squared over 2 on the left-hand side, and T of x squared over 2 on the right-hand side. So if I add s squared over 2 plus T of s squared over 2, what I get is 1/2 x minus T of x squared over 2. Now, let me write this condition. Let me call it 6. So let me repeat what is here, 7. 7 is telling me that u of x plus v of t of x equal to 1/2 x minus t of x square. If I set u of x, to be x square over 2 minus phi of x, and v of y to be y square over 2 minus v of y. Now, this equation, note that cis is equivalent. So I am going to replace equality by inequality. And if I do that, you see that it is equivalent to u of s plus v of y is less than 1/2 x minus y squared. And so this means that u v belong to uc. That implies by 7, if I integrate u of x plus v of t of x mu naught dx, I get 1/2 the integral over rd of x minus t of x squared mu naught ds. But if I use that t pushes mu naught forward to mu1, I see that this is j of uv. So as I've been saying several times, the graph of j is below the graph of the Monge course. Therefore, if they intersect somewhere, it means that at this point we have a minimum for the graph of the Monge course. Hence, t minimizes equation 2, which is the Monge problem. So let me solve one of the homework problem because I will need it to prove that t is a metric. W2 is a metric. So this is W2 of mu naught mu1 square. There is no distinction on Monge problem and Kantorovich problem when mu naught is absolutely continuous with respect to Lebesgue measure. Theorem. Let mu be a probability measure of bounded second moment. Then there exists mu epsilon, absolutely continuous with respect to Lebesgue measure, such that mu epsilon is also of bounded second moment, and the limit when epsilon goes to 0, the Wasserstein distance between mu epsilon and mu equal to 0. So I can approximate any measure by a measure which is absolutely continuous in the versus time distance. So the mu epsilon is explicit. Let rho be a standard modifier, be such that 0 is less than rho, 0 is less than rho. The support of rho is the closed Borlog center 0, radius 1. The integral of rho of x ds is 1. And set rho epsilon of s to be 1 divided by epsilon to the power d rho of s over epsilon. Set mu epsilon to be mu rho epsilon convolution mu dx. So clearly, rho epsilon convolution mu is a function of class C infinity. So if I compute the second moment, we have the integral over Rd of mu epsilon of x dx is the integral we have mu epsilon of Rd is the integral over Rd of rho epsilon convolution mu of x ds, which is the integral over Rd ds, the integral over Rd of rho epsilon of x minus y, mu of y, d mu of y, now I use Fubini. This is the integral over Rd mu dy, the integral over Rd rho epsilon of x minus y dx. But because this is 1, this integral is 1, rho epsilon is a probability density, and so this is 1. Because that integral is 1, and so I am left with the integral of d mu, and the integral of d mu is 1. For the second moment, also, the integral over Rd of s squared mu epsilon ds is the integral over Rd of s squared rho epsilon convolution mu epsilon ds this is the integral over Rd of s squared ds, the integral over Rd of rho epsilon of x minus y mu dy. And again, I use Fubini to say that this is the integral over Rd of mu dy, the integral over Rd of x minus of x square rho epsilon x minus y dx. Now I can compute this So let me compute just this one here. So set z to be x minus y. Then the integral is the integral over Rd of x. This is z plus y square rho epsilon of z dz. I replace rho epsilon by what it is. It is 1 over epsilon to the power d, the integral over Rd of z plus epsilon plus y square rho of z over epsilon dz. So dz is dz multiplied by 1 over epsilon to the power d is a d of z over epsilon. I make another change of variable, call this w. And that one I can write it as z over epsilon by epsilon. So this is the integral over Rd of w plus y epsilon w square rho of w dw. And we are done. Because this is less than epsilon square, the integral over Rd of w square rho of w dw plus twice the integral over Rd of y square rho of w dw. But I can take y square out, and I get the integral of rho w, which is 1. So what I have here is I have epsilon square by a constant plus y square. Since mu has its second moment bounded, this thing is finite. And so I have that mu epsilon is less than infinity. Okay. So this is less than the integral over Rd. According to what I wrote there, it is 2 epsilon square, the integral over Rd of w square of w dw plus 2y square mu dy. And this is finite. Okay. Now I need to prove this. Define gamma epsilon on Rd cross Rd by, if I want to define a measure, I just need to know how to integrate a function. By definition, I set this to be the integral over Rd cross Rd of f of xy rho epsilon of x minus y mu dy dx. Let us compute. This is the definition for all f which are continuous on Rd cross Rd and which are bounded. In fact, to define this, to define a measure, it is uniquely defined if I take the f to be of compact support and continuous. Now, let f be a function of the only the first variable. We have the integral over Rd cross Rd of f of x, gamma epsilon ds dy, is, by definition, the integral over Rd cross Rd of f of s, rho epsilon of x minus y, mu dy dx. I use Fubini to say that this is the integral over Rd mu dx dy f of x, the integral over Rd of rho epsilon of x minus y, mu dy dx. But this is mu epsilon of x ds. So that is the integral over Rd of f of x, mu epsilon of x ds. This proves that the first marginal of gamma epsilon is mu epsilon dx. Also, for the second marginal, the integral over Rd cross Rd of f of y, gamma epsilon ds dy, is the integral over Rd cross Rd of f of y, rho epsilon of x minus y, mu dy dx. I use Fubini again to say that it is the integral over Rd of f of y, mu dy, the integral over Rd of rho epsilon of x minus y dx. But rho epsilon is a probability measure. I can substitute maybe the change of variable. X minus y is w. So I'll have the integral of rho epsilon w dw. That integral is 1. And so I get that this is the integral over Rd f y mu dy. This proves that gamma epsilon s, gamma epsilon has mu epsilon ds and mu as marginals. I can use that to bound the Monge course. Hence, and so W2 square between mu epsilon ds and mu is less than the integral over Rd cross Rd of c of x, which is 1/2 x minus y square gamma epsilon ds dy. I am going to replace gamma epsilon by its definition. This is the integral over Rd cross Rd of x minus y square rho epsilon of x minus y mu dx dy dx. I use Fubini again. This is the integral over Rd mu dy, the integral over Rd of rho epsilon of x minus y square dx. Now I make the change of variable w is x minus y to get that this is the integral over Rd mu dy, the integral over Rd rho epsilon of w square dw. But I can compute what is here. It is the integral over Rd of 1 divided by epsilon to the power d, rho of w over epsilon, w square, dw. I can take 1 over epsilon to the power d inside the dw, so I get dw over epsilon. To produce w over epsilon here, I divide this by epsilon and multiply it by epsilon square. So now we have established consequently, w squared between mu epsilon and mu is less than epsilon square, the integral over rd of w z square, rho of z dz. And so I have an estimate which is even independent of w. Therefore, the limit of w2 mu epsilon mu goes to 0. Okay, so once I have done this, when I want to prove the triangle inequality, it is enough to prove it for smoother function. So if I want to show that this is true, I am going to approximate mu naught by mu naught epsilon, mu 1 by mu 1 epsilon, mu 2 by mu 2 epsilon. So if I know the triangle inequality for density which are absolutely continuous with respect to Lebesgue measure, thanks to that theorem, when I let epsilon go to 0, I have it for arbitrary measure. So now I can state the theorem. W2 is a metric on the set of probability measure of bounded second moment. So proof. Let mu naught, mu 1, mu 2 be in RD. First, W2 of mu naught is less than the integral over RD cross RD of x minus y square mu naught ds dy. But S equal to y, mu naught cross mu naught almost everywhere. So this is 0.
Okay, so there is this factor 2x scalar y, and just to replace this will be, of course.
Yes, so let me take a gamma equal to identity, cross identity, push forward mu naught. Okay. Gamma naught dx dy, where gamma naught is identity, cross identity, push forward mu naught. Then if you compute the gamma of B, this is mu naught of x, such that identity of x is in B. This is mu naught of x, such that S is in B. So this is mu naught of the diagonal of B. And so S equal to Y gamma naught almost everywhere. So this is equal to 0, where I set mu naught to be identity cross identity, push forward mu naught. If I can show data for every mu naught, mu1, W2 of mu naught, mu1 is less than W2, mu1, mu naught, then it means that both expressions are equal because mu naught and mu1 are arbitrary. I just substitute mu naught by mu1. So let gamma be optimal between mu naught and mu1 be such that the distance between mu naught and mu1 square is the integral over Rd cross Rd x minus y square gamma dx dy. So let gamma be a minimizer. I am going to define gamma bar. Define gamma bar on Rd cross Rd by the following: the integral over Rd cross Rd of f of xy gamma bar dx dy equal to the integral over Rd cross Rd. So what will be the guess for gamma bar? Gamma send mass from x to y. I want to define gamma bar, which is going to send mu1 to mu naught. What will be the guess? Interpolation. So if you do an interpolation, so you know how to go from S to Y. If you do an interpolation, it will be between X and Y. You want to go from Y to X. So by definition, I will say this is f of yx gamma ds dy. We have, I want to check what is the first marginal of gamma bar. The integral over Rd plus Rd of f of x gamma bar dx dy equal to the integral over Rd cross Rd. So this is my g of x. So f of xy is g of x. If I write f of yx, this will be g of y. So this is g of y gamma dx dy. but this is the integral over RD cross RD of G of S gamma dy dx ds dy. Sorry, I can just stop there and say that this is the integral over RD G of y mu1 dy. So, the first marginals of gamma bar is mu1. Similarly, the second marginal of gamma bar, you find that it is mu naught. Hence, the distance square between mu1 and mu naught is less than the integral over RD cross RD of x minus y square gamma bar dx dy. But when I integrate something gamma bar, it means that I need to change the order yx. So this is the integral over RD cross RD y minus s square gamma ds dy. And you see that this is W2 of mu naught mu1 square, because the norm of x minus y is the norm of y minus x. Finally, the triangle inequality. To prove the triangle inequality, thanks to the above approximation, theorem, it suffices to prove the triangle inequality when mu naught, mu1 are absolutely continuous with respect to Lebesgue measure. Because if they are not, we approximate them by absolutely continuous Lebesgue measure, and then we prove the triangle inequality for this measure, and we pass to the limit. Let T S be from RD to RD, be optimal in Monge problem, be Borel map, such that T pushes mu naught forward to mu1, S pushes mu1 forward to mu2. Because mu1 and mu2 are absolutely, mu naught and mu1 are absolutely continuous with respect to Lebesgue measure, there is a unique minimizer in Monge problem. So I can write, and the distance square between mu naught and mu1 is the integral over RD of x minus t of x square mu naught dx. And the distance square between mu1 and mu2 is the integral over RD of y minus s of y square mu1 dy. So T pushes mu naught to mu 1. S pushes mu 1 to mu 2. S composition T will push mu naught to mu 1. Indeed, if you integrate f of S composition T d mu naught, then this is the integral of G of T if I set G to be F composition S. So this is the integral of G of T d mu naught. Because T pushes mu naught forward to mu 1, that is the integral of G d mu 1. Now replace G by definition. It is F composition S d mu 1. Now S pushes mu 1 forward to mu 2. This is the integral of F d mu naught. So I see that T composition S pushes mu naught forward to mu 1. Observe that this is identity minus T, the L2 norm with respect to mu naught. Okay, let me go slowly. And W2 square mu 1 mu 2 is, I am going to use the fact that T pushes mu naught forward to mu 1 to say that this is the integral over Rd of T of x minus S composition T of x square mu naught dx. So I have used the fact that T pushes mu naught forward to mu 1. And this is nothing but the L2 norm of T minus T composition S, the L2 norm with respect to mu naught.
So you have proven already that if they are absolutely continuous with respect to the Lebesgue measure, then the Wasserstein distance is given by, no matter which measurable map takes one measure to the other, it's given by that one.
Yes, this is the first corollary I stated at the beginning. So I stated the corollary where I said the optimal gamma in Kantorovich problem is gamma T, where T is the unique optimal map in Monge problem. And so this is another way to say that the Monge cost and Kantorovich cost are the same.
So so these T and S are as offset. Now I understand. So they are such that they realize also the
yes.
Wasserstein distance. Okay.
Yes. So call this 8 and call this 9. By 8 and 9, if I look at the L2 norm between identity minus T composition S, mu naught, this is less than identity minus T. The L2 norm, mu naught, plus T minus S composition T, the L2 norm, mu naught. But by 8, the first expression is the Wasserstein distance between mu naught and mu 1. And by 9, the second expression is the Wasserstein distance between mu 1 and mu 2. But this is always bigger than the Wasserstein distance between mu naught and mu 1. And so we have the triangle inequality. Hmm?
Mu naught with mu 2.
Mu naught, mu 2, yes. So let me make a remark which I am not going to prove. Take the set of probability measure on RD. Take the set of probability measure of bounded second moment. I am going to define a topology on each one of them. Here, mu n converges to mu, mean the integral over RD of phi d mu n. This limit is the integral over RD of phi d mu. And it is very important where I choose the phi C0 of RD. Here I'm going to put a topology. Mu n converges to mu, mean the limit over n, the integral over RD of phi d mu n equal to the integral over RD of phi d mu for every phi in CC of RD, union a specific one, phi naught of S is S squared. So the difference between the two topology is I added one function to the second topology. So it is well known that there is no metric which corresponds to that topology. So you cannot find a metric on the set of probability measure on RD such that you have convergence in that metric if and only if you have with star convergence. However, what is true is the fact that I am adding this function make this topology metrizable, and the metric is the Wasserstein distance. So saying that a sequence of measures converge with respect to the Wasserstein metric is equivalent to saying that this equality holds for all test functions of compact support plus one specific function, which is S squared. So let us now get closer to our Fokker-Planck equation. Subset of the Wasserstein manifold. So this is a manifold in a weak sense, not in the usual geometry sense. So fix U in RD, theta greater than 0, and look at the set of F from RD to 0 plus infinity, Borel, such that the distance between F and the Dirac mass at U is d theta. So as I said, it is easy to show that the distance between the Dirac mass if I take the mean of F, it is easy to see that this is the variance of F. And I am going to impose also that the average is fixed. So I am taking a subset of the infinite dimensional sphere. Okay. So we all know that in infinite dimension, if you take the sphere and you take the weak convergence, it is not closed. So if you are minimizing a functional on that sphere, you take a minimizing sequence, the functional may go straightly inside your ball, and you don't have a minimizer. This set has some interesting property. We study with Eric Carlin, we study the restriction of the Wasserstein distance to this sphere. And we find that it is the arctangent of the ambient distance. So it is exactly the same formula as what you have in the finite dimension. In the finite dimension RD, if you restrict that to the sphere, the metric you get is the arctangent. Here is a non-trivial problem. Let F naught, call this M U theta. Take F naught in M U theta and define I of F to be the Wasserstein distance between F naught plus H, S of F, where S of F is the integral of F log of F over RD. And H is something which is positive. So when you minimize this functional on this set, you find a minimizer easily. Standard method of your calculus of variation gives you existence of a minimizer. But if you minimize it on this restricted self, I don't know of any direct method which is going to give you existence of a minimizer. So we had to use, with Carlin, we had to use a duality argument to prove that there exists a unique minimizer. So I am not going to try to write the proof. What I am going to rather do is assume you know a minimizer. Can you connect that to Fokker-Planck equation? So here is the question I want to address. Problem. Assume F1 is R mean of I of F over M U theta. What is the Euler-Lagrange equation? What are the Euler-Lagrange equation? Satisfied by F1. So the answer is the Euler-Lagrange equation will be the discrete Fokker-Planck. And what I want to do is to show that it is the discrete Fokker-Planck. So you need to learn how to differentiate such a function. So the central point is learn how to differentiate goes to IF. So let us look from a very purely abstract point of view. Assume I give you a manifold M. I give you a function on I from M to R. And I of M not equal to V infimum. So when I want to differentiate my function, if I can differentiate my function I, then the differential will be 0 at M naught. So what I am going to do, first, I am going to take V naught, a tangent vector, at M naught. And I am going to look at the curve exponential M naught T V naught. So this is the geodesic curve passing through M naught and of direction V naught.
What do you mean by this tangent space in M naught?
If I have a Riemannian manifold?
Ah, see, as a Riemannian manifold.
Yes. So I am making an abstract demonstration, how usually you differentiate a function.
No, but you have this Riemannian structure given by what?
No, I assume I am given a finite Riemannian manifold.
Okay.
And I am saying when you want to, if the Riemann manifold was RD or a Hilbert space, I just don't need to justify. Yes. So now I am not on a flat space, and I want to comment on how I differentiate a functional. So you take a tangent vector, you take the exponential map. So the exponential map is the geodesic passing through S naught and of direction V naught at time 0. And you write that T goes to I exponential M naught TV. If I call this alpha of T, at n, it's minimum at 0. So you conclude that alpha prime of 0 is 0. And in fact, alpha prime of 0 will be the differential of I at M naught applied to V naught. And that will be your Euler-Lagrange equation. So I would like to do the same thing here. So to do that, I may need to understand what are the geodesic on the Wasserstein space. The calculation I am going to make, in fact, I am going to use geodesic, but you don't need to know that they are geodesic, meaning that I am going to come up with some magic curve because I know that they are geodesic, but you don't have to know that they are geodesic to make this computation. And in fact, when we started to make this computation, I made it in some work. Jordan, Kindler, and Otto, who were the first people to connect the Monch-Kantorovich theory to PD, also made this computation. At that time, we didn't know what the geodesic on the set of probability measure were. But later, many people realized that, in fact, we were using geodesic. Okay, so I want to find such a curve. geodesic. That is for your curiosity. It is for your curiosity, but you don't need to know that they are geodesic in the calculation. Fix mu naught, a probability measure on RD. Let phi be a function of compact support of class infinity in RD. Consider the mapper set T of V to be V plus T, the gradient of phi of V. This clearly is a converse function, the gradient of a converse function. So when I differentiate Tt, I get identity plus T, the second derivative of phi. This is a symmetric, first. Second, because this function is smooth, the second derivative is bounded. Therefore, if t is small, this is bigger than 0. And so Tt is the gradient of a converse function. Set mu t to be Tt, so identity plus t, the gradient of phi, push forward mu naught. This is a geodesic of minimal norm in the sense that if you compute W2 mu t mu naught mu s plus W2 mu s mu t, this is W2 mu naught mu t. If 0 is less than s, is less than t, and t has to be taken that t is less than t naught, and t naught has to be taken such that this is greater than or equal to 0. Then I have a geodesic. However, here is a concern. Assume I take mu naught on this sphere. Assume that I take mu naught on this sphere. Okay, you can even see that already in the finite dimensional case. This is my sphere, and I take mu naught here. There I am describing a geodesic in RD, not a geodesic on the sphere. If I take a tangent vector pointing inside the sphere, immediately I leave the sphere. So when I want to write the Euler-Lagrange equation, I have to use the curve. Not only we start at f naught, but I have to make sure that this curve stays on this manifold. So what I am going to do, concern mu t is not in mu theta, even if mu naught was on the sphere. So I have to learn how to project on the sphere. I am going to define. So here is the solution. Define mu t bar. This is the projection m, u theta of mu t. And now I am in business. I have a curve which is on the sphere, and so I can differentiate along that curve. So what I am planning to do next is when I have an arbitrary measure, how do I project it on the sphere? We are going to write an explicit formula for the projection. But in fact, you don't need to know that it is a projection. You only need to know that it belongs to that set. In the calculation I'm going to do on Monday, I am only going to use that my new curve on that set. You don't need to know that it is a projection. However, the way we find it was we were looking for the projection on the sphere. Projection. Let F be a probability density of finite second moment. Okay, so I compute UF, set UF to be the integral of V, FV dV, and theta F, recall that it is 1 over D, the integral over RD alpha V minus UF square F of V dV. Okay. I recall the definition of UF and theta F. I don't know that F is on this set, and I want to replace it by another probability density which is on this set. So set, magic. A is the square root of theta F over theta, and F bar of V is A to the power D, F of A, V minus UF plus U. Then I claim that this new function is on my sphere. Okay. So if you don't, if you wonder how could I guess that, do exactly what you will do in finite D. Assume that you have a sphere and you have a point which is not in the sphere. How do you project it on the sphere? You can write an explicit formula for the projection. Now, once you know that explicit formula, how do you adapt it here? The operation which to lambda associate lambda V on RD correspond to the following operation on the Wasserstein time space. It corresponds to the operation which to lambda associate F lambda, where F lambda of V is 1 divided by lambda to the power D, F of V over lambda. Okay. So anytime I want to see the analog of this operation on RD, this is the analog of that the operation on RD. Now the operation with to V associate V naught, V plus V naught on RD, the translation. What it corresponds to? It corresponds to the operation which to V naught associate F of V naught, defined by F V naught of V is F of V minus V naught. So once you know, you understand the similarity between these two operations, if you check how you find the projection on RD, then it gives you an idea how to find the projection on the Wasserstein space. If I don't know that, I say, assume by magic, I write this function. Let me check that it is a projection, and let me check that it belongs to this set. In fact, checking that it is a projection is not very complicated, but it is going to take me 15 minutes. Let me just check that it belongs to that set. We have U F bar is the integral over RD of v f bar of v dv. This is the integral over Rd of v. F bar will replace it by a f of a v minus u minus uf plus u dv. And you see that it is suggesting I set w equal to a v minus uf plus u, so that w minus u over a plus uf is v. Okay? So if I make the change of variable w equal to a v minus uf plus u, it corresponds to v equal to that. And dw is a to the power d dv. So that is the integral over Rd. This is a to the power d. It is the integral over Rd of w minus u over a plus uf. And f of w dw. So that is, when I integrate this, I get uf over a. When I integrate that, I get just u over a plus uf. So it looked like what I had to do is this. And so I do this. And so this is u. Okay, so we have that uf bar is u. Now we have to compute the second, standard deviation. I need the same change of variable formula. So similarly, theta f bar, let me multiply that by d. This is the integral over Rd of v minus uf bar square f bar of v dv. That is the integral over Rd of v minus uf bar. So uf bar is u square. F bar is a to the power d f of a v minus u plus uf dv. And as before, what I did was w equal to a v minus u plus uf. So w minus uf over a plus u equal to v. So this is the integral over Rd. I'll replace v minus u by w minus uf over a square. And this will be f of w dw. So you see that this is d times theta f over a squared. But you replace a squared, 1 over a squared is theta divided by theta f. Therefore, this is d theta. And so it proved that the standard deviation of f bar is theta. So you see I have a very explicit formula. Now let us come back. I am not going to make this computation today, but let me tell you what needs to be done. Ft is identity plus t psi push forward f1. So it was f1, and let me call it f1t. And this is the gradient of a function. Gradient of 5, so that we have a convex function. Now, let's read what this is saying. This is saying f bar of v equal to the determinant of the gradient of L of v, f of L of v. If I set L of v to be this, then the gradient of L of v is the a by the identity, and so the determinant is a to the power d. That means that L pushes f to f bar. Or I can write f bar pushes. I can write the inverse of L pushes f bar, f to f bar. So I want to define f bar 1t. It will be the push forward of L t inverse f1t. But I can write explicitly what is LT inverse. It is given there. LT inverse of W, it is W minus U F1t divided by A F1t plus U. Okay. So I have my explicit mapper here. I have this explicit map. I can compute F1t. Let me give a name to this. This is KT of W. Then if I take the mapper KT, composition, identity, plus T psi, this map is going to push F1 forward to F1T bar. And so this is what will be my exponential map. So again, we prove with Carlin that if you take a geodesic in the ambient space and you project it on the sphere, you get a geodesic on the sphere. And so this is a geodesic on the restricted manifold, although you don't have to know data to do your computation. So we have an explicit formula for our map. It remains to compute the average of f and the standard deviation. But the average of f is easy. U f1t is the integral over Rd of v f1t of v dv. This is the integral over Rd of v plus t psi of v f1 of v dv. So this is uf1 plus t, the integral over Rd psi of v f1 of v dv. And you do the same thing for a theta f1. So you obtain a map which will be a polynomial of degree 2 in T. You plug that in the entropy, you plug that in the Wasserstein distance, you have an expansion of order T, and we tell you how to differentiate. So what I'm going to do on Monday, I will make this computation in detail. And once we have that, we'll compute the Euler-Lagrange equation of the minimizing problem. I'll stop.